All right, I'm going to get started. We are at the top of the hour. Good morning, everyone, and thanks for joining us today. We are going to have an advanced water softening training, and we're so glad you're here. Before we get started, there's just a couple quick housekeeping items. If you would all, thank you. If you would all mute your microphones so we can avoid background noise while Bill's presenting. And if you have any questions, feel free to drop them in the chat as we go. We'll also leave a bunch of time at the end for an open Q&A. So on that note, Bill, let's go ahead and get started.
All right. Can you hear me all right? I look okay?
Fabulous.
Thank you very much. Last month, we talked about basic water softening, and we're going to use this to build upon some of the things that we learned last month. It's going to be a case in progress. We'll just keep going and going and going. Just to talk about what we talked about last month, just to bring up some thoughts about what are the two common hardness minerals. Just want to make sure we've got that covered. The lady in the back with the Hawaiian flowery shirt, is that a macaw on there? That's very cool. What do you think? What do you think the answer should be? Calcium and magnesium. You're exactly right. These are the two that cause the most problem. And why are they a problem? So why are there hard water? Why is hard water a problem in the home? Well, one reason is it forms a soap curd. So what the heck is a soap curd? Soap curd's an insoluble grayish white scum that forms when soap reacts with the calcium magnesium in the hard water. It's technically a metallic soap precipitate that leaves rings around the tubs, dulls fabric, significantly reduces lathering. Basically what's happening is the hardness is preventing the soap from dissolving properly, so it loses its cleaning power and it leaves a sticky residue instead of a lather. You've heard about people talk about how things are squeaky clean, how you're so clean that you're squeaky clean. Well, what that really means is that you've got a soap curd problem, and if you had a water softener, you wouldn't be squeaky clean. You would be nice and silky clean. Another problem with hard water is lime scale buildup. So why is that a problem? This is where it really starts to cost money. Water's not as hot as it used to be, running out of hot water in the shower, turning up the thermostat, spending more money on utilities to get the same results. It restricts water flow, meaning less pressure or flow coming out of the shower head, upset family members I lost something. Hang on. Where am I now? Yeah, where did it go? Because somebody took control and changed it.
We're seeing line scale problems on the screen.
Yeah, but I lost the presentation. Somebody took control for a second and then it. Okay, there it is.
There we go.
Got it back. I got it.
All right. No pushing buttons, people.
Yeah. That includes me. So when the family members run out of hot water, cutting their shower short, or no hot water for the next person in the shower, eventually it's going to cause premature failure. Again, nuisance problems building up in the pipes, or heat exchanger problems. Basically, what happens when anytime you heat hard water, or cool it for that fact, but if you heat it especially, get it hot, it starts to plate out. It precipitates onto surfaces. So you've got a heat exchanger surface in there that you're putting water to, or electrical to, to heat the water inside the tank. As that exchanger becomes coated with this hardness, it acts like an insulation. So it requires more power to do the same job, costing more money, and again, headed for premature and expensive replacements. So how do we correct the hardness? What are we going to do about it? For our purposes, we use ion exchange water softening, taking out the calcium and magnesium and putting the sodium back in its place. Remember the demonstration about the monkeys and the trees? Those of y'all that were there will appreciate that. The monkeys, the apples, and the bananas. It's a pretty good narrative. If you want to talk about it, give me a call sometime. So, what's an ion? Why do we care about what an ion is? An ion's an atom or a molecule with a net electrical charge. So, what are two different kinds of ions? Two different kinds would be cations and anions. Cations have a positive charge and anions have a negative charge. So what is calcium and magnesium? What are they? Are they cations or are they anions? They are indeed cations. How do you know? How do you know they're cations? What's a way to remember that? The name, right? Calcium, magnesium. Remember we talk about cations or being cats, and cats are positive. And then when you pet a cat, you get a big old fat cat jumps up in your lap and you're petting that cat and you're going, and he's purring away and you're just going, You can remember that the cations, the cats, all end in calcium, magnesium, sodium, potassium, barium, strontium. Anything that ends with an is a cation. Just little extra tidbit there. All right. This week we're going to take what we built on and we're going to talk about some numbers and some basic math. We're going to take it easy. Don't worry, I'll get you through it. But water treatment is a lot of art mixed in with science. There's numerous ways to treat a specific problem, and we are not dealing with an appliance like a vacuum cleaner that'll work anywhere. Water problems are site specific, right? But you ask 10 people how to treat a specific problem, and you'll probably get 5 different answers depending on their area and their expertise. So what I'm going to do is I am going to share some rules of thumb and generalities that I learned from some of the old guys who were mentors in mine when I was growing up in the industry. These are not hard, fast rules. These are rules of thumb. These are cheat sheets, I guess you could say it. But some of the guys that I learned from were some of the old guys. My dad, Bill Hall Sr., guys like Sonny Kamak, Terry Insko, Rocky Hoffman, Warren Muller, Harold Posey, Dick Grace, Willie Molden, Mike Trammell, Moses. These guys were instrumental in what I learned. And in addition, I'm going to share some of the rules of thumb that I've developed over 40 years of learning, of making mistakes, and coming up with guidelines that'll keep you out of trouble. These, they work for me, and I'll offer them up to you, no charge. You can use them as you will. Some of the things that we are going to talk about today is capacity. We're going to talk about salt dosages. We're going to talk about flow rates and velocities and why they matter. Does anybody recognize this man right here? This guy's name is Greg Renicky. Greg is a guy that does a lot of seminars, trainings with WQA, TWQA, other water quality gatherings. This guy is so knowledgeable that he can talk about any subject and explain it in a way that it's easier for everyone to understand. That's how you know that somebody really knows what they're talking about, is because they can put it in layman's terms and they're not trying to impress people with using big terms. But the reason I'm putting his name up there, if you ever get a chance, an opportunity to sit in on one of his presentations, do yourself a favor. You will not regret it. But he made a comment one time about families deserve honest expertise and real engineering when it comes to their water, not just off the shelf equipment or guesswork. So when you're talking about real life engineering, these are some of the rules of thumb that I'm going to offer. When we're talking about capacity is one thing. There's an old 16th century proverb says you can't have your cake and eat it too. Or in other words, you can't have the best of both worlds. Everything in the water treatment business is a trade-off. You're getting best of this or the best of that, but at the expense of the other. This is especially true in the design of water treatment equipment. You may have people that will talk about what is capacity. It's how much resin we need to get through a specific amount of time, a day, a week, hours. A new bag of resin from the manufacturer is fully regenerated and ready to go. You don't have to regenerate it before you use it. The nice thing is when it comes out of the bag, it is as regenerated as it is ever going to be, and you're going to get more capacity out of it. Now, capacity, we keep talking about capacity. Capacity is measured in grains, but what the heck is a grain? A grain is a very, very small thing. Basically, it's a unit of weight that's equal to about 1/7,000th of a pound. But this is how capacity is calculated. Like I said, when you open that bag, fully regenerated, a cubic foot of resin is about 30,000 grains when it's regenerated with the maximum salt dosage of 15 pounds per cubic foot. 30,000 grains, some people say 32,000, some say 35,000. I've always tried to be, I try to give myself a little bit of a fudge factor on these things. I try to be conservative. I find out sometimes that if I'm a little too conservative and say, well, we get 30,000, and the competition may say, well, we get 35,000. Well, they've got a better system than you do because they get more capacity. They don't really. It's the same resin. It all works the same way. It's how it's said. I just like to use 30,000 grains because it gets you close and it's an easy number to work with. So if we want 30,000 grains, which is full capacity to a cubic foot, and we're dosing it, that takes 15 pounds of salt when we regenerate it to get it to that 30,000 grains. Now, there is an efficient setting of 20,000 grains when you regenerate it with 6 pounds of salt. So you're getting 2/3 the capacity, right? You're getting 20,000 grains as compared to 30,000 grains. But you're dropping the salt dosage from 15 pounds per cubic foot to half of that, about 6 pounds per cubic foot, less than half. So there's a big salt savings when you're doing this. I like to fudge that even a little bit more. Anytime you install a new softener, a lot of people try to get right on the tail, right on the knife's edge of using the least amount of salt to get the most amount of water. There is a certain amount of that, but sometimes folks try to get too tight on that. And then the next thing you know, the homeowner's calling and saying, sometimes my water's soft, and then it gets hard, and then it gets soft, and then it gets hard, and then it gets soft, and it's very frustrating. One of the reasons, because people try to get too tight. My rule of thumb, and this is just me speaking, instead of using 6 pounds of salt, I'll bump it up to 8 pounds of salt per cubic foot. It's not a lot of cost to the customer. And the main thing is it'll make sure that their softener works smoothly as expected right off the bat. They're not upset off the bat. If they do come back to you and say, is there a way that I can cut back on the salt? Yeah, there is. And you can do it very quickly out in the field just by pushing a few buttons. But it gives them the opportunity to say, okay, look, we're going to cut it back. If we're still getting hard and soft, let me make a few other adjustments. But the main thing, that's just one of my fudge factors. Yeah. So what? What do we care about grains? We care about grains because we're designing a system and we need to know how many gallons of soft water we're going to realize between regenerations. Now, here's another Bill Hall thing. My rule of thumb, when you're talking about how many gallons per day per person, some people will say 50, some will say 75, some will say 150. My rule of thumb is 100 gallons per day per person. That hasn't let me down so far. And it's an easy number to use. So how hard is our water? We need to know that. It all starts with a test, either with a water analysis or a field test to get some approximate numbers. Regardless of which you use, whether using a water analysis or a field test, when you're designing a system, the hardness should be based on compensated hardness. We're talking about each, I like that graphic. It's 100 gallons per day. So what is compensated hardness? When you're sizing the softener, hardness should be based on compensated hardness, not the number that shows up on whatever test you were using. What it is it takes into consideration minerals and other factors that will reduce its softening capacity. And these things are not picked up on a standard field hardness test. Again, it's a sort of fudge factor. So the way that you compensate for this is if right here, if your test says that the water is somewhere between 1 to 20 grains per gallon hard, you're going to multiply that times 1.1, and that's the number you're going to use for your hardness calculations. As it goes up, the factor gets bigger. 21 to 40 grains per gallon, multiply times 1.2. You get up to 71 to 100 grains per gallon, you're going to multiply it times 1.4. And if you go up to 100 grains per gallon plus, you're multiplying it times 1.5, which means that you say you've got 100 grains per gallon. For our calculations, we're going to use the number 150 grains per gallon, and it's going to change things. But this is going to give you a better shot of making sure you're providing some soft water to your customer. All right. So to arrive at the approximate number of gallons of soft water you can expect to achieve per regeneration, you got to remember your high school algebra. Now, my high school algebra was a lot longer ago than some of y'all's. I graduated 1974 from Wausau East High School in Wausau, Wisconsin. Go Lumberjacks. But remember your high school algebra. We're trying to come up with gallons. So what we have to know is the grains capacity, how many grains are in that cubic foot of resin, and how many cubic feet of resin do you have, and you're going to divide that by the hardness in grains per gallon. So your high school algebra, you remembered you've got common denominator here. You've got grains, those cancel out, that gives you gallons, right? So this is how many, got it. A second here. All right. Next thing we need to know is about flow rate and velocity. Now, a lot of people think it's the same thing, but flow rate is volume. It's the volume of a fluid passing a point in time, measured usually in gallons per minute for our purposes, but it's the volume of a fluid passing through. Velocity is the speed of the flow, how fast the water's moving through the pipe, and that's measured in feet per second. These two are directly related. If you have a constant flow rate, and if you decrease the pipe cross-section area, that's going to increase the velocity. Just like the graphic there, if you've got a garden hose and you stick your thumb over the end of it, the water moves faster because you've restricted the size of the pipe. So if we're talking about flow rate through a cubic foot of resin, flow rate is critical to get the kinetics or the exchange of ions that we have to have. If the flow rate is too fast, we get hardness breakthrough. The water won't be as soft as we expected. Now, keep in mind, resin, it looks like a nice hard round bead, but if you were to look at it under a microscope, it would look more like wadded up chicken wire. A lot of the exchange sites are within the bead, not just on the surface. So in order to get the capacities you expect, the water's got to flow through that bead at a specific rate, allowing it to perfuse through the bead to reach all of the exchange sites on the inside. That's why we can't flow it too fast. But if we flow it too slow, the water's going to channel around the bead. It's going to take the passive resistance and not go through the bead itself. Each one of these situations, whichever we go, it's going to result in poor hardness removal and reduced capacities. So why is that important? Why do you need to know that? A lot of times people are concerned about the high-end flow rate when they're sizing something. When you've got to keep in mind the low flow rate can be just as critical. Suppose you had a 24-inch tank that has 10 cubic feet of resin in it, and you've got an expected flow rate of 40 gallons per minute. That's good as long as the flow rate stays where it's expected. What happens if you slow down the flow rate, for instance, pulling a sample port, as long as that softener is running at the 40 gallons per minute that you're expecting it, everything's good. But if you slow that flow rate down, like if you go over to a sample port and you take just a little bitty half a gallon per minute sample, trickling that amount of water through that bed, you're going to get channeling and it's not going to be as soft. So you're testing it, it's coming out soft. But when you're operating it, it seems to be fine. What I'm saying is you can't always size everything on the high end. You have to take account to the low end as well. So the typical flow rate through a cubic foot of resin for design purposes is 3 to 5 gallons per minute per cubic foot. That's typical. That's what we shoot for. Sometimes you can go as high as 10 gallons per minute per cubic foot in certain specific applications. If there's certain things that you can do, you can go that high. But for general purposes, 3 to 5 is the number that you want to remember. We also talked about the minimum flow rate. Minimum rule of thumb is half a gallon per minute to 1 gallon per minute. I always use 1 gallon per minute again, just because it's easy. So if I'm flowing less than 1 gallon per minute per cubic foot, I am not going to get the kinetics that I would like to have. Velocity. Okay. So that was flow rate. That's what we talked about. So what's velocity and what's the difference? Remember we said the two are related. If you had a piece of pipe 6 inches in diameter and 20 foot long, could it flow 30 gallons per minute? Sure it could, easily. Could it flow 300 gallons per minute? It sure could. The difference is how fast the water is moving through the pipe from point A to point B. That's what velocity is. It's measured in feet per second. Generally speaking, in plumbing, you're going to be looking at somewhere between 4 to 8 feet per second. That's pretty much what it's accepted. If you get above that, you start going above 8 feet per second, 10 feet per second or so, it's going to cause problems like water hammer. It's going to cause excessive noise. It's going to cause erosion of the inside of the pipe walls over time. And it's going to cause an excessive pressure loss that maybe you can't absorb in your situation. Hot water, I'm talking about water that's over 140 degrees Fahrenheit. It's more aggressive than cold water. So therefore, velocities are commonly limited to 2 to 3 feet per second to prevent pipe damage on hot water systems. A quick check, a rule of thumb on accepted flow rate through a pipe is diameter squared times 20. Diameter squared, take the diameter of the pipe, square it, and multiply that times 20. And that will give you a rough idea of where you want that, of how many gallons per minute you're going to get through that piece of pipe. These numbers are based on about a 7 gallon per minute, or excuse me, foot per second velocity. So based on that formula, a 1-inch pipe would be flowing approximately 20 gallons per minute. Will it flow more than that? Oh, absolutely. Will a water softener handle more than 20 gallons per minute? A lot of times they will. But just the water flowing through it is not the same as actually softening it. The limiting factor is going to be the resin, not the water softener itself. 1.5-inch pipe, about 45 gallons per minute. 2-inch pipe, about 80 gallons per minute. 3-inch pipe, about 180 gallons per minute. That was my formula, was diameter squared times 20. If you want to get more specific, for all you geeks out there, gallons per minute would be the constant, 2.45 times the diameter squared of the pipe times feet per second. Now, actually, there's you want to use the inside diameter of the pipe. But when we're talking about the difference between inside diameter and outside diameter, it's a very small number, and we're looking for rough numbers anyway. So I don't try to get that tied into it, but for the folks that enjoy that sort of thing, there's the number. Feet per second is gallons per minute divided by the constant, 2.45 times diameter squared. That way you can work it either way. All right. So we've gone through a lot of stuff, but in conclusion, everything is a trade-off. In addition, proper softener design and sizing's got to take into account several factors, such as capacity, salt dosage, flow rate, and velocity. And additional considerations are gallon per minute requirement, gallon per day requirement, pipe size, drain size, hardness, other capacities as well, or other constituents as well. That's pretty much what I had. I would entertain any questions at this time.
There's a couple questions in the chat, Bill. The first one refers to the slides 4 through 6. I don't know if you can get back to that area, but Patrick is asking, do you know time to form the scale pictured and or the hardness concentration?
Come on. I'm getting there.
I was going to stop you, but you were on a roll.
It's not moving.
So I'm remembering
you were
those,
talking about the soap scum and the scale buildup inside the water heater and that sort of thing.
Yeah,
now
there you go.
There's no way of knowing how long that's going to take. The soap scum will show up pretty quick, but this sort of thing it's just going to be a matter of time. How much water have you used? How hard's the water? How hot's the water? How often did you use the water? It's
Is there I know there's a lot of variables. Is there an approximate?
No, ma'am.
All right. There's another question. How does flow rate compare to PSI?
Flow rate always compares to PSI. Generally speaking, the faster the flow rate, the more pressure drop you're going to get. You've got a water inlet that's, let's say it's at 40 psi. You put any kind of water treatment device, whether it's a filter, a cartridge, a whatever, you're going to have a certain amount of pressure loss through that thing as it goes through it. So the pressure drop from the inlet to the outlet side is what we're trying to measure. We want to keep that as small as possible. The faster you flow water through there generally, or the tighter the pipe, which is going to increase the velocity, the higher the pressure drop is going to be. So instead of having 40 psi going in and 38 or so coming out, now you're down to 35 or 30 psi coming out of that thing. And your wife's going to holler at you because the water's just dribbling out of the shower head, and it's I'm not getting the hot water that I used to get.
Another one regarding flow rate, it says, how are flow rate and velocity easily determined in a typical home? Is there an easy method to use?
The flow rate is going to be what I always use is just the pipe size. You know, I mean, somebody else say, well, how big a house is it? It's a 3-bedroom, 2-bath house. So therefore we've got used to be a 3/4 inch water main feeding those things. Now it's becoming more like 1 inch because the houses are getting bigger. Generally, we've got, instead of 2 bathrooms, we got 3 bathrooms. Another thing to keep in mind is a lot of the newer high-end homes have multiple shower heads in the master shower. They've got these full body washes. Some of those things on the high end can use like 30 gallons per minute if you've got them all cranked up. So therefore, you're checking the pipe size also. That is a 3-bedroom, 2-bath house, but they got an 1.5-inch water meter going to that thing. Why is that? What's going on, ma'am? That do y'all have high water usage devices that we're not aware of? And she goes, oh yeah, we've got these shower heads. These are cool, you know. And but that's going to take into account. So this is where flow rate with a home is going to be your best bet is asking a few questions and take a look at the pipe size.
Yeah, so I think that also would answer. The next one is, how do I know the velocity?
You're not really going to know the velocity. We use the 7 feet per second guideline as so we can determine how many gallons per minute will a piece of pipe flow. Like I said, if you've got a 2-inch pipe, you can flow that thing. You can flow 100 gallons per minute or better through it. But we want to maintain it down to about 7 feet per second. And by using 7 feet per second, that was my formula at diameter squared times 20. We'll get you right there. So you don't really need to know the specific feet per second that's flowing through that house. We're going to use that more as design criteria.
All right, looks like there's one more maybe. If a slightly oversized water softener and carbon system is installed in a home, example, a 2 cubic foot unit in a 1-person, 2-bath home, is channeling a concern due to low water use, or is that exclusively controlled by DLFC?
The drain line flow control. Now it's going to be service flow rate, not the backwash flow rate. With a home, it's kind of a game of averages. You know, sometimes you're using a lot of water at one time, sometimes not so much. And as long as it kind of goes back and forth and up and down, it's not that critical in application. In a commercial application, it may be more of a problem. But as long as you're exceeding that 1 gallon per minute, and this is not for carbon, this is for resin, exceeding that 1 gallon per minute per cubic foot guideline, you're going to get the proper kinetics. You go below that, you're probably not going to get as much.
Bill, would
yes, sir.
Would having iron in the water or other things like silica, and in that same situation where you have low use of the water, would that make channeling a little more aggressive?
A little more prevalent. Yep,
yeah,
sure would.
Okay.
Very good. Well, that's all the questions in the chat. If anyone wants to unmute themselves and ask a live question, you're welcome to. Bill is ready. Bring it on.
All right, I got a hardness question. All right, okay. Mr. Del White has a hardness of 120.
120 grains per gallon?
Uh-huh.
Okay. So my first question to him and say, how did you get that number? Did he use a field test kit? Did he have a water analysis? How did he arrive at that? If he's using a field test kit, keep in mind that those things, you start getting pretty far out there, 100 grains per gallon, you're getting 100 drops to turn it. You may want to dilute that test. Sometimes it's not as going to be as precise at the higher ends. Regardless, ask him how he got the number. And if he says, I had a field test or something, ask him, did you compensate that number? And he's going to say, I have no idea what you're talking about. And you can get into it if you want to. Just say, okay, look, for these purposes, because there's a lot of things that don't show up on the regular tests that will affect the capacities, we're going to use the number of 150 grains per gallon on our calculations on sizing the water softener.
Okay.
In addition, keep in mind that if you're at 100 grains per gallon or so, if you're over 50 or so, you're not going for salt efficiencies at that time. Well, we were talking about running things a little lower capacity at lower salt dosages. The higher the hardness is, you're going to have to hit it with, you're not going to have a choice but to hit it with 15 pounds of salt per cubic foot.
Okay, I'll let him know that. Thank you.
We did have one more question come in the chat. Does a wider diameter tank have higher flow rate and contact time than a narrow tank with the same capacity?
Not necessarily. You've got to, there is a balance. Like I said, everything's a trade-off. And when you design how many cubic feet of resin are you putting in a specific tank, you go by bed depth. You have to have a certain amount of bed that the water's going through to give it the contact time so that it can do its thing. So a bigger tank, a bigger diameter tank, you're still going to need a certain amount of resin in there. You can't put the same amount of resin, whether it's a tall, skinny tank or a shorter, squattier tank. You have to put the proper amount of resin in that tank for that size. So you're not, I don't really see we're comparing apples to apples unless I'm misunderstanding the question.
Perfect. Anybody else? Is higher gallons per minute required for more cubes of resin to backwash?
Yes. Your backwash flow rate is going to be based on so many gallons per minute per square foot of bed area. And the bigger the tank, the more bed area, the more gallons per minute it's going to take.
Anyone else? Got another one. Is there a cheat sheet available with this information?
Like I said, a lot of these rules are things that I came up with over the years. There's nothing that, I've got notes and stuff like that in my hand script writing that nobody else can read that I've got. But I also that's why I tried to put some of those numbers in this presentation. So if you wanted to go back and look at it, you would have them there.
And there are some sheets available, some specification sheets that might be helpful on our chargerwater.com. If you go to the top of our homepage, there's a link up there that says for professionals. And on the very beginning of that page, you'll see a bunch of links. to different PDFs that you can download and use that might be helpful with this kind of information. And if there's something you're looking for, let your branch manager know, your local branch manager, and maybe it's something we can come up with for you. Don't know till you ask. We're always here to help.
Next month, we're going to change gears a little bit and talk about RO. We're going to talk about point of use RO. We're going to start real basic. And if this is something y'all are interested in, I'd love to see you there. And if I'm